In this video, we will talk about some of the methods for determining rate laws experimentally. There are several different types of experimental methods that we can use to determine rate laws. Of the ones that are possible, the most common two are the isolation method and the method of initial rates. In the isolation method, we use a vast excess of all the components except one. We then monitor that one component as it changes with time. The reaction then becomes what's called a pseudo nth order reaction, where n is the order of the lowest concentration component, the one that we are tracking. So if we have our rate being equal to our rate constant times a to the m and b to the n, if we flood the reaction with a vast excess of b, then essentially b becomes a constant, right? If we have 100 times as much b as we have a, then if the reaction goes to completion, we'll have used up all of our a, but only 1% of the b, right? As the reaction goes to completion, right, all the a is gone, but because there was 100 times as much b as we needed, only 1% of it was reacted. So to a large extent, the number didn't change. So what we can then do is lump all of our constants together and come up with a new rate constant for the pseudo nth order reaction. We have our old rate constant times the concentration that we're using for B, and because we're using a vast excess of B, it doesn't change. So this whole part here is a constant, so we can lump it into a new constant. Our equation then simplifies to rate is equal to K prime, our new rate constant, times a raised to the m. This dramatically simplifies our equation. And if we imagine that we have multiple different components like a C, D, E, and F, if we make it so that all the components except one are in vast excess, then we can probe and look to see how that one component changes while maintaining the other ones as being the same. The other method that gets used is the method of initial rates. For this particular method, the initial concentrations are varied. To do this, you have to do multiple trials where you're changing the concentrations of each component one at a time. It can be done in combination with the isolation method, although it doesn't have to. The rates of two trials are divided by each other in order to cancel out some of the variables to make it so that we can solve our multivariable equations. We will go through an example of this process in just a little bit. We can then take the results and plot them on a log-log plot to work out the rate of our different components, to work out the order of our reaction, to see how things vary with temperature. We can do all this sort of stuff with the method of initial rates. The problem with the method of initial rates is that it will typically miss effects that products can have on the rate law. In a previous video, we were looking at the rate constants and the units associated with them. Within that particular slide, there was this part where we were looking at the rate law for the reaction between hydrogen and bromine. And the rate law was fairly complicated, and it actually had the products in the rate law. So a lot of times when you form products, they can actually inhibit the reaction from continuing towards completion. If you're only looking at the first couple seconds of a reaction, you won't have built up much product, and so you will miss these effects. You won't be able to see whether or not there's an intermediate or a product that has a substantial effect on the rate. So the problem with the method of initial rates is it doesn't look at the effect that products or intermediates can have on the rates, right? Those get totally missed via this method. So let's now look at how we would use this method of initial rates to determine the rate law for a particular reaction. So let's say we have our reaction here. We have two reactants. So what we're going to do is we're going to propose that our rate is equal to some constant times our concentrations of each one of our components, so NO, raised to some power, and I'll call this A for the power of NO, the order of NO, and our other reactant is O2, and we'll raise it to the B power. Okay, so what we're trying to do is we're trying to find the rate law for the reaction. So we need to know what K is, we need to know what A is, and we need to know what B is. We want to know the order of the reaction, so that is A, B, and then the order of the overall reaction is A plus B. And we want to know the specific value for the rate constant, so we need to figure out what K is equal to. Okay, so the problem that we run into immediately is if we look at any of these trials, we know what the rate is. So we have this value. We have our concentration for NO initial and our concentration for O2 initial, right? So we essentially have these two values. So we got one equation, but we don't know what K is, we don't know what A is, and we don't know what B is. So we have one equation with three unknowns, which is unsolvable. However, we can do a little bit of math trickery to be able to reduce the total number of unknowns. As long as we're doing the reaction at the same temperature, the rate constant, which is temperature dependent, stays the same. If we don't change the temperature, then the rate constant stays the same. So what we can do is we can take a couple of these trials and divide our expressions by one another. So what I mean by that is what we're going to look for is two trials in which the concentrations of one of our components stays the same. So I'm going to start with looking for one in which the NO changes and the O2 stays the same. The reason I'm doing that is just because NO is the first one that I wrote down. Okay, so I'm going to take, if I look, trial 3 and trial 1 have NO changing value and O2 staying the same. NO goes from 0.03 to 0.06, and O2 is 0.0055 and 0.0055. So those numbers are the same. So I'm going to divide the rate of trial 3 by the rate of trial 1. And trial 1, so if I take rate of 3 over rate of 1, that is the same as taking K times the concentration of NO for trial 1 raised to the A power, O2 for trial 1 raised to the B power, and then the concentrations for the top would correspond with trial 3. Okay, the reason that we're doing this is because the concentration for O2 is the same, they will cancel each other out. And because the K is temperature dependent and we're not changing the temperature, our K values cancel out. So these two K values are going to cancel out. We now have one equation with two unknowns, A and B. And because we've selected our concentration of oxygen to be the same, that will also cancel out. So I'm going to write out this expression with our concentrations in there so we can see how they cancel out. So this would be 0.06, that quantity raised to the A, divided by 0.03 raised to the A times 0.0055 raised to the B, 0.0055 raised to the B. So because the values with the B are the same, they will cancel each other out. So now I have one equation, rate 3 over rate 1 is equal to our value for NO raised to the A power divided by our value for NO for trial 1 raised to the A power. So I now only have one unknown, A. So I can plug in my values for rates, try to figure out what A is. The problem we run into is that A is up in the exponent. Now, because we're taking the ratio of two values raised to the same power, this is the same thing as the individual values raised to the power. 0.06 over 0.03 is equal to 2, so this whole thing is 2 raised to the a power. If I plug in my values from my rightmost column, the rate values, from trial 3, this is 3.42 times 10 to the negative 2. For trial 1, it's 8.55 times 10 to the negative 3. Okay, the ratio here is equal to 4. Right? If you plug this part into your calculator, you're going to get a 4. So essentially 2a is equal to 4. Now, if we're ending up with whole number values, a lot of times you can actually figure out what a is going to be if you know your powers, right? 2 raised to the second power would be 4, and so we know that a is going to be equal to 2. But if the ratio of the concentrations don't give you nice whole numbers, a lot of times you're not going to know what the power is going to be. So if like the ratio here was maybe 1.5, 1.5 raised to the second power is less easy to calculate in your head than 2 is. So if that's the case, or like we said before, the order of the reaction doesn't have to be a whole number, right? So you could be having a value of maybe -1 or 3/2, 1/4, something that's not a whole number. The way that you can figure this out is by using one of the rules that goes along with logs. So one of our helpful log rules is that the log, or the natural log, of x raised to the n power is equal to n times the natural log of x, right? So we can get access to the power by taking the natural log of both sides. So if we take the natural log of our value for our rates, rate 3 over rate 1, this is equal to a times the natural log of the concentrations. If we go generally, the concentration of NO, trial 3 over concentration of NO, trial 1. So this would be the natural log of 4, right? That's rate 3 over rate 1, is equal to A times the natural log of 2. We can then move the natural log of 2 over to the other side. So we get, divide both sides by the natural log of 2. On the right-hand side, the natural log of 2 cancels out. So this gives us A is equal to the natural log of 4 over the natural log of 2. And if you plug that into your calculator, we get A would be equal to 2. Okay, so now we're going to try to solve for B. I'm going to look up here and I'm going to use trial 2 and trial 1. I'm going to put trial 2 on top, and the reason I'm putting trial 2 on top is when I get to this step here, where I'm taking the ratio of the concentration, if I have the larger number on top, I'm more likely to get a whole number, which makes it easier to eyeball the order, although it's not always going to work out the way we would like. But you have a better chance. So I'm going to take rate of trial 2 divided by the rate of trial 1, and that would be equal to K times NO for trial 3 raised to, well, we know that A is now a 2, so we can just put a 2 there. And O2 for trial 2, and this would be trial 2. We still don't know what this one is, so we keep it a B. Okay, we can put K here, NO for trial 1, that's a 2, O2 for trial 1, B. Okay, so our K's are going to cancel out, right, because we're doing it at the same temperature. If we plug in our values, our NOs we will see cancel out. So this is 0.030 divided by 0.030 raised to the second power raised to the second power times O2 trial 2b O2 trial 1b. Our 0.03 raised to the seconds cancel out. This is the same thing as our values raised to the b power. So this would be 0.0110 divided by 0.0055 raised to the b. So this is essentially 2 raised to the b. A lot of times when you're doing the method of initial rates, what you'll do is try to select your concentrations such that they double. And the reason that you use doubling is because a lot of times knowing your powers of 2, 2 raised to the second power is 4, 2 raised to the third power is 8, makes it much more likely that you're going to be able to just eyeball it. But again, it's not guaranteed. Okay, so here we have the rate of 2 over the rate of 1. So this would be equal to 1.71 times 10 to the negative 2 divided by 8.55 times 10 to the negative 3. So this is actually ends up being a 2. So we got 2 raised to the b is equal to 2. Therefore, b is equal to 1, right? So that worked out. We could also do the same thing that we did up here, where we take the natural log to find our b value. But because we know the value, we can just use b as is, right? So it worked out fairly well for finding b. A is located right there. So our expression, our rate law, is rate is equal to K times the concentration of NO raised to the 2 times the concentration of O2 raised to the first power. So that is the first part, figuring out the rate law for the reaction. Right? This is the expression. The order of the reaction is going to be the sum of our exponents. So the order is going to be equal to 2 plus 1, right? The 2 plus 1. So the overall order is going to be third order. This is second order with respect to NO, first order with respect to O2, right? That's what the exponents are. The 2 goes with the NO, so it's second order with respect to NO. The O2, the oxygen, we figured out that our B value, right, was 1, and so it is first order, or a 1, with respect to the O2. Third order overall, second order with respect to NO, first order with respect to O2. Now the last thing that we need to do is figure out what the K value is. So what we can do is use one of our individual trials to figure out K. In order to do that, however, I'm going to need to free up a little bit of space. Okay, so to find our K value, what we will do is we will rearrange our equation to solve for K. So we have rate is equal to K times the concentration of NO raised to the 2, concentration of O2 raised to the 1. To solve for K, we divide both sides by our concentrations. That will move them to the left, and we get K is equal to rate divided by NO raised to the 2 times O2. Okay, so we can just take any one of our trials and plug in the values. So let's try, trial 1. It's the first one, so why not? So that's 8.55 times 10 to the minus 3 moles per liter second. Our concentration of NO, so this is moles liter times seconds. Concentration of NO is 0.030 moles per liter, right? That is concentration. This is squared times concentration for O2, 0.0055 mole per liter raised to the first power. Okay, so if we plug this into the calculator, you're going to get 1727.273. Okay, in terms of the units, we have moles per liter on bottom here. That will cancel out that mole. That liter will cancel out that liter. And so we're left with 1 over seconds divided by moles to the second power, liters to the second power. So because the moles per liter is in the denominator, to move it up, it's kind of like flipping it. So that gives us liter squared per mole times seconds. In terms of significant figures, our concentrations each had two significant figures, and so our end answer is going to have two significant figures. So this would be equal to 1.7 times 10 to the third liter squared mole squared seconds would be our end answer for our K value. All right, so that is that one. Our overall expression, this part here, would be the rate law. And then our overall order was 3, which comes from down there.